will be done by Dani. Dani used to be at ATH Zurich, and now he's in the Department of Civil and Environmental Engineering at the University of Nevada, Reno. And we're grateful that he's here with us today.
Thank you, Jordi. I asked Jordi to make it short, but I didn't realize it would be this short. So, good morning, everyone. Welcome to your second day in paradise. Today's talk will build a little bit on some of the concept that Rene introduced yesterday, and also Thomas. And we'll talk today about the unsaturated state of porous media. In other words, if yesterday we focused on groundwater and on saturated state, here will be on unsaturated state, in which we have coexistence of water and gas within the porous medium, and that gives rise to a whole bunch of processes that I'll collectively call today capillary processes, but they're not only capillary processes, as you'll see later on. The scale, it would be largely small scale. I don't want to say pore scale because I do work with, I'll present concepts that involve already the REV that we heard about yesterday, but it's largely focusing on a small scale as opposed to, say, the catchment talks we heard about in the afternoon yesterday. My talk will focus on the role of water, water retention, and so on. I'll give you an outline in a second. And the following talk by Kino will focus on mixing, again at this similar scale of pore scale and beyond. And so this will be complementary, and I'm sure you'll hear more during the week on other angles of the same phenomena that I'll be presenting today. So we'll talk about the domains. What is soil, vadose zone, and critical zone? I'll try and place those in context because we hear them and not always clear what that means. We'll talk about fundamentals of surface tension and liquid-solid interactions in soil and porous media in general, but I'll focus on soil. When I say porous media, I'm thinking soil, but of course, when Rene says porous media, he thinks fractured rock, and so these are all geologic porous media. I'll focus on soil. We'll talk about wettability, capillary rise in cylindrical and angular pores, dynamics of capillary rise, interfacial jumps, stuff that happens at drainage and wetting fronts. That will be interesting because yesterday we heard a little bit about inertia, and today I'll try to hammer that a little bit more. We'll talk about, I'll try and avoid that. We'll talk about soil water characteristic curve and a very important function and the parametric models that we use to characterize soils with different soil water characteristics. You know, we heard Van Genuchten model, Brooks and Corey model, and other models that we use in hydrology. A little bit about adsorption and water films at the dry end of the soil water characteristics, and if I have time, I'll talk about the aqueous habitats that microbial life experiences in soil and how it's related to capillary processes. And if I still have time, I'll say a few words about capillary forces and unsaturated soil mechanics. Okay, so that's the plan for today. Please feel free to ask questions, especially students. And I'll try and place if you heard these topics before, I'll try and provide some nuggets that will keep it interesting, even though you know the topic. So let's start with the domains that we deal with in a natural system. So you hear about the vadose zone. The vadose zone is basically the zone extending from the surface of the soil to the groundwater. The soil itself is in humid regions typically synonymous with the vadose zone, but not always. So in arid regions, this vadose zone can extend a few hundred meters, and so there is a distinction between soil, the top maybe 2 meters of weathered rock and where life is happening, roots are existing, and the vadose zone that can be unsaturated but extending a few hundred meters. And then to add a layer of complexity, we define the critical zone, and that one is extending from the top of the canopies of a forest, for example, down to the bottom of the active water table. If you ask me what that means, I have no idea because nobody knows what the bottom of the water table is, but there are some operational definitions in which water that sees the surface or interacts with the surface within certain time horizons. The difference between these, all of them imply meeting of the atmosphere, lithosphere, hydrosphere, and the biosphere, meaning this is a meeting place where life is interacting with the solids, with the water, and basically they are critical or important because of this life supporting function, which is one of the themes of this summer school. So I'll come back to this definition if we need to, but in general you have now a concept or situated in which compartment we talk about when we talk about veda zone, soil, and critical zones. Oh yeah, one more comment before I forget. The critical zone typically takes on longer time scales. So we're talking about processes like we heard yesterday from David and Camille, almost geomorphic time scales. So it's not only hydrologic time scales that we usually do when we talk about soils or veda zone. And they look about larger scales. So typically when you talk about critical zone, you invoke scales typically of catchment and beyond. Okay, so these are the kind of distinctive features of this domain. Just to highlight the importance of these domains for life support, I'll mention some boilerplate language we use when we talk about how soil is important. It provides anchoring and growth media for plants, which are most of the biomass on the planet. It serves as a water reservoir and a functional water purification system, although it carries at any given time less than 0.5% of all the fresh water on the planet. It actually contributes, as I said, to a very large fraction of the biomass. There is still the ocean side of the story, but in terrestrial system, it supports most of the biomass with this 0.5% of the fresh water, which is quite impressive. It is nature's recycling system. It supports most of the global biogeochemical cycles, nitrogen, carbon, phosphorus. It provides habitats to the largest number of species. So if you put the DNA on the planet in a different compartment, the largest compartment will be in the soil. And it also, we build our houses on it, we have our airports on it, and so on. So it serves as a substrate upon which we have our life. There is a bit silly, I think, economic analysis for how much it will cost us to provide these services. It's like how much will cost you to buy oxygen if you needed to breathe. So that's basically the same logic, but maybe it's useful to place this in context and have a bit humility when we think about the services we get from soil. And so this guy's estimated $100 trillion per year the worth of these services. I have no idea how they come up with this number, but in any case, the point they're making is that the total global GNP is less than that. So if we had to pay for these services, we would not be able to afford it. That was more or less the message. In any case, it just highlights the importance of this compartment of the biosphere to life on the planet. And many of the processes I'll be talking about play into that functioning of the soil that we try to kind of list here as enumerate here. So now bring me to the role of water in soil and some of the definition of the water potential. And I'll take it from René's definitions yesterday. As soon as water interact with a porous medium, and everybody who gives a lecture on porous medium should have an object like this. This is a piece of sponge. So I have here free water in a cup. I cannot hear it, but it's free. I dump this porous medium into that free water, and what happened is that this water now become part of this sponge. It's no longer free. Okay, I have some extra here, but I'll pretend there is none. What happened is that now the water is held by interaction between the solid surfaces, the capillary, the pore spaces, and so on. And to release that water back to its free state, either I have to dry this sponge, so I put thermal energy into it, or I have to apply mechanical energy to squeeze it back and release it from this lower state of energy that the water is experiencing when it enters this porous medium. That's the entire concept of water potential. How much energy I have to apply to squeeze this water and bring it from its captured state to a free state. And so formally what this means is that in lawyer language, it would be the amount of work that infinitesimal amount of water at equilibrium is capable of doing when it moves to a standard reference state. We're agnostic about whether the work is positive or negative, and that's why we can afford to say capable of doing. In this case, I had to apply work, mechanical work, to squeeze the water. Otherwise, so I put a minus sign in front of it, the amount of work that I have to apply to release that water. The water, as soon as it is imbibed by the porous medium, it becomes subject to different force fields. Not all of them are force field. We have gravitational component, meaning that if I take this sponge and put it vertically, water will drain from the top to the bottom of the sponge. So there is the effect of gravity on this water. There is a metric or capillary potential, component of the potential, that I'll talk about today. That will be the main topic of today. There is pressure potential. Sometimes there'll be a positive pressure on the water within this porous medium. And there is a solid potential, meaning if there are interfaces and there is solutes, or there is appreciable amount of salt outside those interfaces, there'll be a component of potential that can drive water either out of, say, membranes of cells or plant tissue, or sometimes there'll be a potential that the interface need not to be a biological membrane, can be an evaporating surface that also acts a membrane, because salts do not evaporate but water evaporates, so we have another component of water potential. So the assumption is that the total water potential, which is an important number, important quantity, because that defines the gradient for transport of water in unsaturated porous medium. So remember that it's not going to be just a gradient of metric potential. It will be a gradient of metric potential plus gravitational potential and sometimes solid potentials that will drive water either in or out from point A to point B. That's something to remember. The other peculiar thing about this component of potential is that the metric potential and the pressure potential are mutually exclusive. So I'll talk about the metric potential in a minute, but when the soil becomes fully saturated, the metric potential is 0. And if it becomes positive, the metric potential remains 0. But the pressure potential takes off. Metric potential exists in the negative side of the range of potential, and I'll explain in a minute. One comment about the definitions that Rene presented yesterday. We can express, indeed, soil water potential as energy per unit mass. So while saying infinitesimal amount of water, I did not specify if it is volume, mass, or weight. And so we can now express it as amount of energy per unit mass, per unit volume, or per unit weight. And they have different terms or different signs. I don't know if everybody can see the table down here. Good. So we can call it the chemical potential. If it's energy per mass, it's usually expressed in units of joules per kilogram. If it's energy per volume, we end up with Newton per meter square or pascals. And if it's energy per weight, we end up with units of head, lengths of meters. Okay? And these quantities are related to each other via the relationship between volume, mass, and weight. Questions so far? So these are just the definition. Yesterday we heard that, where is this guy? Yeah, that King Hubbard was the person that defined the water potential, and I was holding my tongue not to say anything yesterday because Rene was right into it, and I thought maybe I should set the record straight. And the record is that Buckingham in 1907, and if you read the language, it's actually beautiful. It's a quotation from his paper from 1907 saying that let a small mass of water, delta theta, pulled away from the soil so as to reduce its water content by delta theta, obviously. let psi delta theta be the work that we have to do to pull this water away. Then we may define psi as the work required per centigram to pull water away from the mass of soil. We shall call psi the capillary potential of the soil. So it cannot be more clearer than this. And so I kind of... All right. So actually, Buckingham was very, very prolific. Those of you who do fluid mechanics, they know the pi theorem. That was this guy, Buckingham. Those of you who do rheology can look at the first solutions to Bingham flow were done by Buckingham. He wrote stuff on Stefan. Anyway, he was very prolific. He was one of this generation that were trained as undergrads at Harvard, and then go to Europe to do their PhD, because Germany was then the center of science at the time. So he did his PhD with in Heidelberg with some of the leading physical chemists of the time. So he was very, very versed in thermodynamics, and so he could borrow this concept of potential and bring them to the porous media studies without having to worry about vectors and so on, because these are integrative quantities of energy state, and that was, I think, a revolution. Okay, enough with Buckingham. Back to the metric potential. As I mentioned, this is the fellow that we'll be focusing on in this talk today, the contribution and the origin of this component. It is, as I said, operates from 0 for a saturated soil to minus infinity for totally dry soil. Think of it as the temperature scale. You all understand that minus 100 is much colder than minus 1, and that's basically how you should think of metric potential. The more negative it is, the drier the soil. Okay? All right. The component of the metric potential are of capillary origin, and we'll focus on that, and textbooks mostly focus on that. But also there is a component of adsorption that is liquid-solid interactions, but we typically don't tend to focus on, and I'll try and highlight it in today's talk. So remember, when I talk about metric potential, we lump these two together because we don't have a way to separate this, to measure this independently, but we recognize that these are really two independent components, and sometimes, especially when the soil is dry, one will dominate over the other. You can imagine that, just visualizing how water is held in soil. Okay, so what factors affect the metric potential in soils? So we'll group them as interfacial processes: surface tension, contact angle, surface roughness. Then we'll talk about geometrical factor, curved interfaces, sizes of pores, and we'll talk about capillary rise. And then we'll have more interfacial processes to talk about the adsorption part of the component of the metric potential. Starting with the surface tension, you may have seen it already. When we have an interface, an abrupt boundary between one phase, in this case water, liquid water, and air above it or vapor above it, there is an imbalance of forces that molecules at the surface experience. Typically, you would have a molecule in the lattice experiencing. Sorry, I don't know what's going on with this. I'm pressing the wrong direction, but in 5 slides at a time. and so typically we'll have. Okay, so let me step back a little bit. A water molecule has 2 hydrogens and 1 oxygen. Electrons that orbit this molecule spend more time around the oxygen than they are around the hydrogen, and so we have a slight imbalance in charge. So we say that the oxygen side is slightly negative, and the hydrogen side is slightly positive, and that gives rise to formation of very, very important class of bonds that we are super critical for biology, and that's hydrogen bond. That is, the hydrogen on one side of the molecule attract itself or bind itself temporarily with the oxygen of another molecule. And if you look at the configuration, you can have 4 such bonds forming on average within the lattice of water. Now, these are not permanent bonds. These are it's not covalent bonds that you'd have in other chemistry. So these are very temporary bonds, and they constantly break and form. So we call the water the flickering lattice, meaning that bonds are forming and breaking. And in fact, there is an insane amount of molecules that would leave the surface of the water and also come back to the surface of the water. So in picosecond, the residence time of a molecule at the interface of water is about picosecond. It's a very, very short duration. And so the system is in constant state of change. But on average, we have 3 hydrogen bonds at the surface here and 4 hydrogen bonds within the bulk of the water. And so to bring a molecule to the surface is energetically unfavorable. I have to break at least 1 hydrogen bond, and who else will not. And so the result is that the surface of water at the interface between the water and the gas behaves like a skin. The ramifications are that it takes energy to bring molecules to the surface. So extending that surface is energetically, you have to invest energy. Think of blowing air into a bubble underwater. Second, the surface itself, because of the energetics of this, tries to minimize itself. And so water will find ingenious ways to wrap itself around surfaces at a minimum surface interfacial energy. So that's very, very important, because a lot of the capillarity phenomena are dependent on this minimization process that water experiences when it is at the interface. I want to point out that a similar concept of this abrupt change between molecules that sit in a bulk versus molecules that sit in a surface also applies to solid gas interfaces. And so they have excess free energy at the surface. And so the surfaces tend to behave slightly different, I don't want to say slightly because I don't know, different than the bulk behavior within the solid. And so there'll be energetics that is associated with any interface between phases, okay? Here are some values of surface tension. It is expressed as energy per unit area, joules per meter square, or force per unit length. If joules time meter is Newton divided by meter squared, then we end up with a Newton meter. So these are two ways to express surface tension. There is direct link between the value of surface tension and other properties. I'll just mention the enthalpy of evaporation, but there could be other properties that are linked to this behavior of the interface. So, for example, polar molecules, say evaporation from water, I can relate the value of the heat of vaporization, if you know what I'm talking about, with these properties of the interface, and relate, say, the heat of enthalpy of the enthalpy of evaporation from water to ethanol, for example, just based on the polarization that they have at the surface. So here are some values for different liquids. So this is liquid gas surface tension. For water, it's 0.07 newtons meters, or 72.9 millinewton per meter. For ethanol, it's about 1/3 of that. Interestingly, mercury also has a surface tension, although it doesn't have hydrogen bonds. So the hydrogen bonds are not necessary for this phenomena, but rather having a different molecular environment at the interface than the bulk liquid. In this case, mercury is a liquid metal, so the bonds are typically metal bonds. The surface tension, I'll try and stop doing it. You get a look ahead at the slides. So the surface tension of mercury is about 7 times that of the surface tension of water. You may have already know something about mercury in terms of other phenomena, wettability, and I'll talk about it. But surface tension has nothing to do with that for this part of the talk. And that brings me to wettability. That's another class of interactions between the liquid and the solid. So when you place a liquid droplet on a surface, Let's assume that the liquid droplet is being spread over the surface because it likes to wet the surface. We'll come back and say what that means. At some point, the forces that pull the liquid to spread it are opposed by the tendency of the interfacial air-water interface, if we're talking about water droplet. That interface do not want to be extended any further, and then there is a balance of forces. The balance of forces between the tendency to spread the liquid droplet over a surface and the resistance of the air-water interface give rise to a balance of energetics, where we increase the area of the droplet by covering what used to be a gas-solid interface with a solid-liquid interface. So they have their own values of energetics of the interface. And adding at the same time an area with the surface tension of the liquid-gas interfacial energy. And so at some point, we have if you want, the partial derivative of the energetic reaches a maximum, or the derivative is zero. And we have this relationship that include in them the energetics of these surfaces and something we call the contact angle. And rearranging this, you end up with this famous equation by Young. The contact angle of the line between the air liquid and the liquid solid, right at the contact line, there'll be a particular angle that reflects the balance of these forces. It's been recognized, I think it was 1805 by Thomas Young, and we'll come back to Thomas again. These are manifestation of how these droplets look like. You might wonder where this cosine of the contact angle comes from. It's basically just a tangent to the air-water interface intersecting the flat surface. So the interesting thing about this phenomena is that I'm explaining it by molecular arguments. This is energetics of the surfaces, but the manifestation is completely visible at almost any scale, well, even to the eye. And there are very few phenomena that has their origin in the molecular level, but they are also visible macroscopically. It's a very, very remarkable phenomena related to this wettability. So we can classify liquids and solid surfaces by their tendency, for example, of the liquid to wet the surface. So we call it, for water, we call it hydrophilic. Water likes to spread over the surface. Or sometimes for certain surfaces, the surfaces will be hydrophobic. The water does not like to spread itself on the surface, and it kind of curls and creates a minimum interfacial energy of, say, sphere, which would be the minimum interfacial energy for a droplet. We classify those hydrophilic and hydrophobic relations based on the contact angle. And so if the contact angle is less than 90 degrees, we call this pair hydrophilic. And if the contact angle is larger than 90 degrees, we call it hydrophobic. Okay, it's arbitrary in a way, but it's very useful. For example, when you look at mercury, I don't know how to do it without. If you look at mercury, it actually wets glass with it's hydrophobic, or not hydrophobic, mercuryphobic. There's no hydro in mercury. So it's mercuryphobic. It forms a contact angle of about 150 degrees sitting on glass. So I guess a point to make here is that the surface tension and wettability are not surface tension doesn't necessarily explain wettability. Okay, so there in wettability I have the energetics of the surface, the energetics of the interfacial area, and all of this need to come to balance. So surface tension alone is just one component of the three energetic system. Okay, good. Now that I need to move. Yeah. What happens when the surface is heterogeneous? Meaning, what if I have a surface that is dotted with hydrophobic grains, and the rest are hydrophilic grains or surfaces that are chemically altered to have a combination of hydrophobic, hydrophilic. Well, for that we have some intuitive equations like the Casey or Casey-Baxter equation that set the angle of cosine of the contact angle of material A and the complementary of the fraction with the contact angle B. Cosine of the contact angle B. So that's for material A and B that is dotted on the surface. The amazing thing is that both the droplet surface and mostly the contact line knows how to optimize this and come up with an effective representation. You can run models and so on, and the contact line just knows it naturally. Of course, because it's a molecular force, it's a molecular phenomena, so it happens at the smallest of scales of the material. For example, if you look at placing a droplet on a porous surface, or if you entrap air bubbles under air pockets under the surface, and so the modification of the contact angle from say Young's equation would be that I'll use the porosity of the surface to weigh the one part of the equation and the one that is associated with the liquid gas, because the liquid gas now is sitting on the bottom, divided by the surface tension of the liquid gas. So porosity becomes a parameter for characterizing the effective contact angle of droplets sitting on porous surfaces, be it a mesh or a screen or even entrapping air, as I'm showing here in this nice image from Escher. Okay, is it clear? Good. So let's talk about what happens when the surface is rough. When the surface is rough, the effective contact angle, according to Wenzel, is simply the ratio of the roughness times the original contact angle. So it's a bit problematic because we cannot have a cosine greater than, or absolute value of the cosine greater than 1, our cosine greater than 1. So we cannot have a cosine here in absolute value greater than 1, either -1 for hydrophobic or 1 for hydrophilic. So that's one thing. Second, people have wrote papers and papers on how limited this Wenzel equation is. Sorry guys, I'll keep on doing it until I get the hang of it. Because of the roughness, the contact line has actually have many configurations in space, and so there is not a single contact angle, but a multiplicity of those. Anyway, long story short, is that the Wenzel equation is the Wenzel equation is a reasonable approximation, provided that the roughness is small relative to the size of the droplet, so it becomes correct for infinitely large droplets relative to the roughness, and as long, of course, it doesn't violate the relationships here. So it's an approximation, probably useful for small levels of roughness, but not too much. Yes?
So what is A? This is the ratio A by A smooth.
So A is the area that is generated by the roughness. So I'm showing it here in 2D, but you can have it in 3D.
Like some periods of roughness.
Well, you can do actually the analysis, the rigorous analysis of the validity of this is usually done on a period of sawtooth or pillars. And it's basically the effective area of the footprint, say, of the droplet relative to a flat surface.
So smooth is something different.
Yeah, so the ratio would be 1 if the surface was smooth, and to be higher than 1 if the surface is rough.
So smooth is a reference.
Yeah, exactly. Smooth is a reference, and for that we have the original relationship that. Okay. Okay, so that's what happens with wettability. In fact, nature capitalized in material science capitalized greatly on this phenomena in developing these super hydrophobic surfaces by manipulating the roughness. So this is other than gravity that distort a little bit the droplet, it's perfectly sphere. And so you can imagine, I think Bicot and Quéré from Paris were contracted by Reno to produce windshields that shed drops, so you don't need wipers. It's basically automatically hydrophobic, and so rain doesn't stick to the windows. You can imagine that somebody will pay a few more euros to get that. And of course, the relationship also of heterogeneous surfaces were tested with mixtures of grains of hydrophobic and hydrophilic, and we get very nice correspondence with this theory. So these are not necessarily rigorous equations, both Casey, Baxter, and Wenzel, but they are very good approximations for practical applications. Also, nature knows about this somehow and manipulates the surfaces of leaves to remain dry or hydrophobic. For example, a good example is the lotus leaves that basically through some special structures on the surface of wax pillars, they allow droplets to basically roll from the surface of the leaf and actually clean it from dust. So this is really a nice dust cleaning mechanism that the lotus leaf has to keep the leaves, from, because it's a flat surface sitting on lakes and so on. Other plants use this strategy to keep the leaves also dry. So because it is very important for the gas exchange of these leaves with the atmosphere, and being dry is an advantage. Okay, let's talk about interfacial curvature. One of the key steps in understanding capillarity happened simultaneously in France and in the UK, England, I guess, at the time, in 1805. Thomas Young, that I mentioned earlier in this paper on the essay on the cohesion of fluids, stipulated not only the contact, the emergence of a contact angle, but also the fact that when you have a curved air-water interface, you have a pressure jump across that interface, and the amount of pressure jump is inversely proportional to the radius of curvature. So think of it as a bubble. Small bubble will have much higher pressure than a large bubble in the same fluid or under the same conditions, okay? Laplace, what's his name? Pierre-Simon Marquis de Laplace, at the same time, as a footnote of his Celestial Mechanics book number 10, I think at the time, wrote a footnote about this relationship between pressure jump and curvature. Many historians, especially mathematicians, because I read a few papers on those, think that Laplace's definitions were much more rigorous, because Laplace talked about, first of all, he formulated in modern mathematics, so it's very easy to follow. He defined pressure, whereas Young was mostly intuitive. He was talking about this from an intuition point of view. There was no single equation, and definitely no discussion of pressure. And so some think that Laplace should actually get credit for this, but we call it still Young-Laplace equation. So Young-Laplace equation basically states that for a given curvature, we have the surface tension, so the pressure jump across the interface will be proportional to the surface tension, inversely proportional to the curvature. Okay? Here's an example of how you can derive it. I would have asked Thomas to derive it on the board with a chalk, but I'll just do it here with the PowerPoint. So the idea is that imagine that I'd like to calculate the pressure in a droplet, in a bubble. I have a piston. I can increase the pressure by delta P, and with that I increase the surface area of that bubble by delta A, right? So I can write a balance equation. This is energy balance in a way. Delta P dV, the change in the volume of the droplet, is balanced or equal to the increase in surface tension in surface area times the surface tension. Okay, so all agree with that, right? Thomas? Okay, good. So we can do some little expansion of what this dV might mean, express it in terms of radius, r. And the same thing on the right-hand side, dA, we can express it in terms of radius r. We drop any dr, because the expansion we can do infinitesimally small, so we can have any dr squared dropped out of this calculation. And with some algebra, we end up with delta P equal to 2 sigma over r. So it's a very general result. I have not invoked any solids in this discussion. This is a property of the interface itself. Of course, we are interested in this phenomena for the cases where the interface wraps itself around solids. And so we can look at a case like this in which water is held between two grains, touching grains in this case. And you may be familiar with this, actually these are images. You may be familiar with the formation of pendular rings of water around these grains. Especially in unsaturated sand, these are very conspicuous, you can see them. And you can apply the Young-Laplace equation, or the Laplace-Young equation, to calculate what would be the pressure inside these liquid domains. The equation is very similar to the original Young-Laplace with a single curvature, except we have two types of curvature here. We have this curvature into the liquid, and we have the meridial curvature in the plane of the contact of the two grains. And so by convention, we assign a positive sign if the liquid bulges into the air. Think of it as applying pressure and pushing that membrane of the interface into the air. And it is negative if the interface, if the air protrudes into the liquid. Think of it as sucking on the liquid to create this curvature. So with this sign convention, you would have to put into the R2 a negative sign here to get the pressure correct. Okay, so we leave it generic here as plus, but actually the sign will depend on the nature of the curvature of these interfaces. And you can do it for any interface. In fact, you can apply analytic geometry to calculate any interface, and there is some very rigorous and analytical formulas for this, but they are not necessary. Since this spherical approximation by Fisher from 1926, it's called the toroidal approximation, it's enough to assume that it is semi-spherical, although it's not exactly correct, to get the pressures correctly. Okay? Questions? Good. By the way, the fact that we calculate the pressure here in this pendular domain can imply, or can imply at some cases that there is a tensile force that keeps these grains together. So you can imagine when I'll talk about mechanics of wet sand, this will be the origin of the forces that allow you to take a dry sand that is completely cohesionless and build sandcastles with it. So the forces will come from here. Okay. Okay, so that brings me to putting it together to the capillary rise model. And this is the idea is that when you put a glass tube in the water, magic happens. All of a sudden, water spontaneously rises through this capillary, glass capillary, which is amazing, right? I mean, why would it do that? Well, it does it, and it's very, very impressive, so much so that the person who published about it the first time, James Durin, this fellow here, wrote the following about this phenomena. He said, some days ago, and I'm reading it from here because here they have this some weird character that makes it difficult to read, but it's basically the text here published originally. Some days ago, a method was proposed to me by an ingenious friend for making perpetual motion. wait, which seems so plausible and indeed so easily demonstrable from an observation by the late Mr. Hauksbee, said to be grounded upon experiment that, and here comes the caveat, though I'm far from having any opinion on attempts of this nature, yet I confess I could not see why it should not succeed. And so the scenario that he had in mind was this scenario here, in which you have capillary rise, and you fold the capillary and it drips back into the liquid. And so, in theory, it should have perpetual motion. Can anybody tell me why it shouldn't work? Okay, you know intuitively that perpetual motion is not possible. Well, what happens? Why wouldn't it drop? Why wouldn't it work? Well, okay, but suppose the capillary is so short that viscosity is not limiting.
The same capillary force that moves it up will not let it drop?
Yeah, but why? Gravity is in our favor, right? I folded the capillary over, and I think he did even some tricks here with the diameter of the capillary. It looks very, very. I don't blame the Mr. Durin for saying, "Oh, why it shouldn't work?" Anyway, yeah, there are many reasons why it shouldn't work. In particular, the fact that as the curved interface that actually create the motion arrive to the end of the capillary, it relaxes the curvature, and there is no longer a driving force. So perpetual motion still is not possible, even with this very compelling example. But I like that. But look what he said afterward. He was a very, very good scientist. He was a strong defendant of Newton at the time, and Newton was under attack for these theories. He was a physician. He was the head of a hospital in UK and published extensively on smallpox, epidemiology. So he was really and was the secretary of the Royal Society for some years. In any case, what he wrote is that but as searches after things impossible in themselves, he recognized this is impossible, right? Are frequently observed to produce other discoveries unexpected by the inventor. So that was very, very nice of kind of a summary of his endeavor into perpetual motion. That he was not able to show that it is actually producing perpetual motion, but he laid the foundation for capillary rise, and that was, I think, his contribution for this presentation here. So what is this formulation of capillary rise? So we stick a capillary with radius r into a liquid. We automatically generate an upward pointing force that is the perimeter of the contact line at the perimeter of the capillary, with cosine of the contact angle and surface tension pulling upward. And what pulls downward, or what stops this process, is the mass, or the weight, of the water, which is pi r squared, the height of the column, the density of water, and gravity. So if we had half gravity, it will go double, or in zero gravity, in theory, it should go some other limit, and I'll talk about that limit in a minute. So basically, this is the basic of the capillary rise equation. We can rearrange this equation and write it in terms of the capillary height is 2 sigma. Sigma is still the surface tension of water, cosine of the contact angle, divided by the density of water, gravity, and the radius of the, inversely related to the radius of the capillary. Okay? If you want to impress your friends, you're sitting in a bar and said, well, I can tell you what the capillary rise of 5 micron is. You basically take h in meters, 15 over the radius in microns. And so if you have 5 microns and your friends say, what will be the capillary rise? You can tell them 3 meters. Yeah, perfect. You see, everybody's impressed. Okay. Okay, so the capillary rise was actually still the model or the vehicle that we interpret capillarity in porous media. Of course, we are not naive to think that all pores in soil or in rocks are cylindrical, but we make some hand-waving equivalents, taking a pore of any shape, assigning to it some equivalent radius, and represent it as a capillary. So we do that with, I think, a bit too much liberty, but still, it is still a useful concept. We can relate, for example, when we see materials with small grain sizes, say clays, versus material with large grain sizes, say sand, we can interpret the grain sizes back to pores and see what the capillary rise would be, and it's actually working quite well. So I did some calculation here using this impressive formula of 15 over r in microns, height in meters, and you can calculate that if you have a sand with a diameter of 0.5 millimeter, 500 microns, typically the pore size of packing of these grains will be 1/3 of the radius or 1/6 of the diameter. You can estimate the diameter to be or the radius to be 80 microns, and the capillary rise will be about 20 centimeters. If you have a silt material with a radius of 4 microns, the capillary rise will be over 3 meters. And if you have a clay with a radius of less than a micron, 0.17, the capillary rise will be about 90 meters in theory. In practice, there'll be other constraints. Okay, so it just allows us to place material soil properties and porous media properties and the capillary rise that you'd expect over these surfaces. For example, if you look at the capillary, the height of the capillary, what's so-called capillary fringe, or the capillary rise above a water table. So there'll be some proportionality. If the material here is sand, it will be, as I said, about 20 centimeters. If the material is silt, it should be 1 meter. If the material is clay, it will be a few meters. Okay? That gives you a bit of context for why this is useful. You can do that also for building materials. I think I took this from my room this morning. No, I'm just joking. So you can have an order of magnitude to kind of guide your thinking just based on a concept that is quite simple, and that's the capillary rise equation. Okay, so I don't know why I'm doing this again, but so far you'll see all textbooks, they talk about capillary rise in a cylindrical capillary, and that kind of like, why is that? So what I like to do is kind of dispel and remove the fear from angular pores. After in the next 2 slides, you'll never worry about angular pores anymore because they are so simple. Okay, so I'd like to look at capillary rise in pores with cross sections, square or triangular, or any shape actually. Okay, so a few things about angular pores. Unlike cylindrical pores, angular pores would allow coexistence of liquid and gas within the same domain. In cylindrical pores, basically, it's like a piston. You either have water or no water. Okay, so angular pores are very important because they are more realistic in terms of water retention in porous media when you drain the pores. They also have some interesting phenomena that you basically pull on that water until it snaps off, as you can see. Well, you could have seen in this. Let's see if I can do it again. Oh wait, so anyway, so you can pull on it and it basically at a known curvature it will snap, and we know that, we can predict that snap off, and so it's not a continuous process of drainage. Okay, it has some reasons, maybe I'll have a chance to talk about them later on, but they are very interesting. They are different than the message is that they are different in their drainage behavior than cylindrical pores, but they are quite predictable. There is nothing unusual about them. Back in the 2000 with Marcus Tuller, and I'm very sorry that I have to kind of show him here because he passed away last month. He was very young, not very young, but he was in his 50s, and so it very saddened me. I don't even know what happened yet. I'm still kind of like a bit of a shock. So with Marcus, we developed some theory that tells us how much water is retained at pores at different curvatures. So you can imagine if I know the geometry of this pore, and I know the curvature of the interface from, say, Young-Laplace equation, I can basically calculate how much water. It's just a geometrical calculation. And you can generalize it with some shape functions or angularity factor. It doesn't have to be a regular shape of angular pore. And you can calculate how much saturation you have in the pore. Let me show you an example here. This is an equilateral triangle pore with the length of 100 microns. I give you that I have a metric head of minus 45 meters, minus 0.45 meters, that's half a meter of suction, so it will have a particular curvature. How much water is in the pore? This is the two-dimensional representation, so it's very easy to calculate. I calculate the area of the water from these formulas that we developed to be, I don't know, 547 microns. The curvature from the Young-Laplace equation is 16 microns, and the angularity factor is 2.05. You can read the equations later. They're not that important. Just the fact that I divide this by the area of the pore, which you can calculate as 100 squared times square root of 3 over 4, and you end up with a saturation of about 12% or 13%. So basically, just in terms of how much water is held in angular pores, you should feel empowered to do the calculation for any shape and any, it's really simple algebra. More interesting, I think, is the capillary rise problem in angular pores. There, basically, I rely on Bicot and Quéré from 2002. They were really, this is a it was a very inspiring paper for me because it also liberated me from the fear of angular pores. And so basically what they wrote is that, oh, there are two forces, one that's pulling up, and that's the perimeter times sigma cosine the contact angle, they're using theta here, and the weight of the water, which is rho g h a squared, that's the water up to here, and then there is some corners here that I have to calculate the complicated integral, and I get the mass of the water that is held by capillary forces, okay? And so you do all this calculation, you end up with 3.77 sigma over rho Ga. If you remember, in a cylindrical capillary, it was factor of 2 here. They dropped the cosine theta because they assume it's completely wettable, but it's not a problem. So for all practical purposes, if you know the perimeter and you know the contact angle and the surface tension, of course you can calculate how much mass of water this capillary force can hold, and the rest is just geometry. So in this case, we end up with about, I can tell you that if you use 4 times sigma cosine theta, you'll be very close to the experimental results. For triangular, I can run the calculation and approximate it to 7. In fact, if you don't believe me, so this is the data of Bicot and Quéré using 4 sigma cosine theta over rho Ga. So fear not angular pores. That's one message. And I asked Charlie yesterday if he can calculate the capillary rise between 4 touching cylinders or 3 touching cylinders. What did he say? Why should I? So he was not impressed. He said, oh, why should I worry about it? Anyway, so the idea here is that if you can, of course, calculate the perimeter. That's very easy, but the area is a bit more complicated. I think it's about 0.85 b. If you do the calculation, 0.85 b squared times h, and you balance it by the perimeter times sigma cosine the contact angle, you'll get this formula here, 4.5 sigma over rho gb. Or for the 3 cylinders, this is important for wetting of fibers or wetting of hair. You know, why hair is kind of, how is it held together and so on. Wet hair, I mean. So that's not mine, but and so these are really the point here is that we can do these calculations. They're as simple as a rise in cylindrical capillary. Just need you to change your thinking about the process. Okay, so far we talked about capillary rise under equilibrium conditions, where we balance surface tension and contact angle with the mass of the weight of the water. But what about the rate of capillary rise? And so I can see here that from a book, I forget, I didn't put the credits here, but that the capillary rise in sand, and we know that sand has a lower capillary rise, but it reaches the maximum within, I don't know, some fraction of a day, whereas for clay loam it will take several days to rise. Why is that? Why would I expect in sand to have the capillary rise faster than I would have, say, in silt?
Because the pores are bigger?
Exactly. So viscosity then becomes now an issue, right? Exactly, because pores are bigger and there is less resistance, velocities will be higher. So let's talk about it a little bit. And so this is the general force balance equation for capillary rise, and maybe there is some dark forces we're not aware of, but we have gravity, we have viscous, and we have inertial forces balancing the capillary drive, if you wish, or capillary pressure. And so what we've done so far is we basically just balance these two terms. We balance capillary pressure with a gravity term, and we end up with this capillary rise equation. Okay, so far. What Lucas and Washburn have done, and I'm going to be regretting doing this again, but anyway, what they've done is that they use capillary pressure balanced by viscous pressure. The idea is that I have a capillary drive, and now as I get more and more liquid, so imagine the capillary is horizontal, there is no gravity. Okay, so it's for simplicity. As I pull more and more water to the capillary, I have liquid that is longer and longer, I have more and more viscous dissipation or friction basically between the liquid and the walls, until at some point I consume all the capillary drive and I reach a balance. And of course along the process, because this is not a jump process but a gradual process, I can calculate how far the liquid penetrates into the capillary as a function of time. And that's basically what Lucas and Washburn did in their equation. And basically so they balance these two forces and a bit of algebra, and you end up with x of t, the length of the water column into the capillary is the square root of time and a bunch of coefficients that include in it not only surface tension but also viscosity. So eta here is viscosity. And of course a function of the radius. So larger radius, faster speed. If you take x over t being this I have to square it. So anyway, I'm not going to square it. So if you take the velocity as x over t, you can see that there is a proportionality with r. The larger r, the larger the speed. Okay. In this paper by Fraser and Dreyer, they did a full analysis of what happens when you introduce the capillary to the liquid, what happens initially in the first few seconds, what happens later on, what happens when viscosity becomes an issue, and then when gravity stops the process. Okay? It's a very nice paper. I like it because it set the stage for what I'm going to do next. And that is that initially, at short times, the height is just a function of t, which means that the velocity is proportional to this term here. And if I plug in, say, radii, different radii for water, if I have a 10 micron pore, at the very first few seconds, the speeds of penetration can be of the orders of 3 or 4 meters per second. If you plot it against a Reynolds number, you get a Reynolds number of 100 or more. Okay, so almost by design, the penetration of water or air-water interfaces into small pores happen at very high rates. And that brings me to the, okay, now what? Yeah, that brings me to this, let's see if I can do this. Oh, of course it's not running. Let's see if I can do.
Can I ask a question, Dan?
Yeah, sure.
Can you comment on the inertia term from the former slide? I didn't fully understand, like the HH dot thing.
Well, the HH dot is basically the inertial term. I will comment on it here, actually. If you look here at this is a 4 millimeter sintered glass bead sandwiched between two glass surfaces. So it's a kind of a helical, porous helical cell. And you can see that the pulling of the water, you'll see that every time an interface penetrates, there is oscillations. And that's a hallmark of inertia. So basically, the interface is trying to dissipate the energy that the inertial jump was imparting on it. And along the process, in this little experiment, we measure pressure fluctuations as well as acoustic emissions. I will not talk about acoustic emissions. It's a story for a different talk some other time. But just looking at the inertial part. And so this is very common. In fact, if you look at the motion of interfaces, so this is again a drainage front from a glass bead pack, you see these jumps. So what looks like, if you zoom out, it looks a very, very benign front that moves down. In fact, it is made up of very violent jumps, pressure jumps, acoustic emission associated with it, and a lot of inertia happening at the front. So all our understanding of how unsaturated flow happening, in which you have viscous creep flow basically, is actually out the window, because when you see these things, you realize that something else is happening at the front. So what is that something else? Actually, it's not new, because Haynes have seen that in 1930s, and people recognize it. In fact, he even proposed this as a mechanism for hysteresis, but everybody kind of dismiss it as kind of, yeah, it's interesting, but so what? So we wanted actually to do a bit more in-depth into this so what, and this is work that we've done with Francisca Mugius, in which we looked at different displacement front, comparing the average velocity of the front versus the average velocity or the velocity of the jumps that are associated with the front. Let's look at it here in this. So the front velocity is somewhere here of the order of, I don't know, 5-10 meters per second. The jump velocities are distributed around 100 to 300 meters per second, millimeters per second. So this is the Reynolds number associated with them are up here. So they are in the order of hundreds. And so this is all happening in a porous medium, which we already classify as, small Reynolds number porous medium. And in fact, at the front, it's not. And of course, that brings to bear the question of what that means for the flow dissipation, what does it mean for mixing, for example, at the front, and things of that nature. So we developed a little model of two capillaries. And basically, when you have a jump, so you have a flow rate, a fixed flow rate, drainage rate from these capillaries. And then when you reach a critical point and there is a jump, the volume of water that is now displaced is larger than Q, and so some of it goes back to the second branch of this pair of capillaries. Okay, that's the basic idea. Do you see that? Okay. And so you can run this model. You can have a mass conservation, that Q, and what happens in the two branches of the capillaries. And basically what you find is this periodic jump, refill, and then withdrawal, and then again jump, refill, and withdrawal. And that's very similar to what you find in the experiment that I showed you earlier. So that is nice, but it's not yet allowing us to make any predictions about the behaviors of fronts. And so we constructed a throat network model. The reason I'm using throat network and not pore network is because at the nodes of this throat there is no volume. So basically liquid is distributed to the other throats as soon as conditions are favorable. And you can see the behavior is quite similar in terms of the jumps to that of an equivalent porous medium. The reason we wanted to do this throat network, not pore network, is to basically be able to see the effect of inertia. Meaning, in the real world, I cannot turn off inertia. I can only turn off inertia when I have a model, so I can compare the outcomes with inertia and without inertia. Okay? And so when you do that, and this is again the inertial term for you, Kevin. When you do that, you end up with several realizations. To me, it was a bit of a surprise, but actually, I should have known better. One is that these are the line without inertia, so this would be the throat radius and interfacial jump velocity, for example, but you can do other metrics. Inertia not only accelerate, but also decelerate, so it has a stabilizing effect. So we think of inertia as an acceleration, but we should not do that. It's a force. It has a deceleration as well. And you can see it nicely by the red points with inertia that are distributed slower and faster than the average line. So that's one realization. Oh no. Anyway, the next thing is because there is an additional force, you have penetration events or invasion events that do not happen without inertia. This is the red area here. So inertia, because it is an additional force, it affects the sequence of pore invasion. So it's okay, it affects a sequence of pore invasion. That's interesting. What does it mean macroscopically? It turned out that macroscopically it doesn't mean anything. So while the details of the invasion without inertia and with inertia are different, when you average them, it turned out that I was expecting that there'll be huge phase entrapment as I change the capillary number or the inertial characteristic and so on. I was expecting huge effects on the entrapment. It turned out that the addition of inertial forces did not, because it has two sides to the force. And so eventually what happened is that the entrapped saturation was similar with and without inertia. It was a huge disappointment, obviously, but on the other hand, it kind of clarified the role of inertia in this displacement phenomena. Okay, I have to speed up a little bit. Okay, yeah.
How do you reconcile it with like the energy loss that you get still measured?
I'm sorry, with what?
How do you reconcile that there's very little difference macroscopically, but still you have much more energy loss?
Yeah. Okay. I don't know how to cascade energy loss into displacement because, you know, we have, for example, oscillations. Oscillations meaning that I dissipate energy without any displacement. So I don't exactly know how to reconcile it in that sense, but it was a surprise for sure because I was expecting that additional force. But because it operates in multiple directions, I don't think it's only two. It ends up being not adding much to the picture of phase entrapment. So geometry, average capillary number would be far more dominant than the addition or omission of inertia.
If I can ask you another question. So here your conclusion on inertia, they are based on glass beads. You have pores that are pretty big.
Yeah.
So will it change the result if you have much smaller pores?
That's a very good question. The bottom line is I don't know, but I can say that inertia will be much more suppressed in smaller pores and not enhanced. And so my intuition is that, we have not tested it, but my intuition is that smaller pores will actually have less impact of inertia than large pores. Just simply because the viscosity, the viscous dissipation will be so much more dominant. And so every time there is another force that dominates, it will suppress the impact of inertia. So it could be that inertia will actually be suppressing stuff that would happen without it. But of course,
It's much faster.
I'm sorry?
The hinge jump is much faster.
Exactly.
Yeah, but of course, in theory, it is much faster, but I'm thinking about what happens to the excess fluid, excess liquid that I'm not draining, so it will be redistributed. And there is a characteristic length over, Reno helped us calculate some decay along the front, how far from the jump I actually feel the pressure jump and stuff like that. It dissipates very quickly. So I on balance, I would say that in smaller pores, I'll have faster jumps, but I'll have much more viscous losses. So I think it will not radically change the picture. That's my thinking. Okay, yeah.
So here you talk mostly, if I understand right, about the unsteady inertial term, like the one that goes to the boundary. Have the Reynolds term as well. Does it matter much here, or is it not really?
I'm sorry, I didn't get the question. I see, you're saying that we're talking about unsteady.
So you have the unsteady term, which I think is what
Yeah.
you're putting into your inertial term, but you have the convective inertial term as well, right? The one that goes with the Reynolds.
Yeah.
So is it important here? Does it play a role? Or is it
No, it's only important for me is to declassify this behavior of the front as a creep flow.
That's
So that was mostly, and I was curious about what is the role of these pistons, in phase entrapment, and of course you can ask about mixing as well, because those jumps are not what you assume when you do the displacement in the standard form, be it macroscopic or otherwise. So I'd like to spend a few minutes left talking about a very important function in unsaturated soil, and that's the soil water characteristic curve. It is a nonlinear function that characterizes different soils. It brings together all the stuff I mentioned about surface area, pore sizes, capillarity, and so on, into a function that relates the amount of water held in the soil versus the metric potential that is associated with that water. So every point here you have to select the water content and read the metric potential. And that's actually how we measure it. We take pairs of metric potential and water content. Once we establish equilibrium, we plot a dot on this curve and we collect all these dots. Of course, this is very important for us to define or to deduce pore size distribution, for example, by taking the capillary, the cylindrical capillaries bundle and deduce pore sizes from it, which is completely wrong, but we still do that regularly. We infer from it unsaturated hydraulic conductivity and a lot of functions about biological life, which I will not have time to cover today. And so it's quite central for understanding flow and transport in unsaturated porous media. Looking at the soil water characteristic curves of 3 different soils, clay, silt loam, and sand, just by looking at them, we can actually make some inferences about the properties of these soils. For example, when the metric potential is close to 0, we can assume the soil is fully saturated. So from these intercepts here, we calculate the saturated water content or the porosity of the porous medium. From the amount of water held at the very dry end of the characteristic curve, we can estimate surface area of these soils. So we can say clearly here, for the same water potential, we have much more water in the high surface area clay soil than we do in sand. From this bending point, we call the air entry value. We calculate the pore at which air penetrates into the soil first. You can think of it as the height over the water table for the capillary fringe that I mentioned earlier. That's another way to interpret this. And from the slope of this curve, we can look at material that has a broad size distribution versus a very narrow size distribution of pores in the soil. So these are all characteristics that will show up in the parameterization that we'll do for this curve, and we use them to characterize different soils. So here's one of the parametric models that we use commonly is the Van Genuchten model. Yeah, 5 minutes? Okay, sure. So this is a characteristic curve, a parametric model by Van Genuchten. The idea is this, that it takes so much work to produce these data points, and some of them are measured by different methods. So we don't have really typically a lot of data points, whereas our models require derivatives and continuity and so on. So this is a place where parametric models like this one fit into this picture. We take a few data points, we fit the parametric model, and from then on, we understand that soil, at least our model understands that soil through the parameters of this characteristic curve. So in Van Genuchten model, we have the relative saturation, theta minus theta r. Theta r is this one, divided by theta s minus theta r. This is the range of water content, is equal to 1 over 1 plus alpha. Alpha is the parameter which is inversely related to air entry value, generally speaking, times the absolute value of h to the power of n, and all of this to the power of m. So, okay, to make things simpler, we use some reduction here. We say m and n are related. So we have 5 parameters: theta s, theta r, 4 parameters: theta s, theta r, alpha, and n. And that's all we need to fit a retention curve to measure data points. And this is what you'll enter into your model. There is another model by Brooks and Corey that was before Van Genuchten. The modelers among you will appreciate the fact that it is discontinuous, and that's really a pain to take derivatives. Yeah?
So, I mean, this Van Genuchten model is, so what you are showing is, let's say, I think it's one direction when you are basically increasing the
Sorry, just say.
content, but I remember like the problem is here also that when you dry it and again increase the water.
Oh, yeah. Okay, so yeah. So what's your name? Richard. He talks about hysteresis. So the idea is that depending on which path you take on a characteristic curve, whether you wet the characteristic curve or dry the characteristic curve, the path is not unique, and you may have loops, meaning certain pores will empty one way but will not empty the other way, and so you'll have some differences in the... yes, but for the simplicity of the presentation today, I thought I'll leave hysteresis out of it. But it definitely exists. There are ways to characterize it, but it is one of those phenomena that everybody knows exists, but everybody prefers to ignore it. Is that? No, I mean, it's really the reality, because we already are stretching our abilities just with this parameterization. And so just to briefly show you what can you do with this parameterization if you're asked to start a hydrology model somewhere in the world. You don't have the data yet. So there are now maps all over the world of these parameters. This is work from our group. Surya Gupta did this. We took all the available retention curves from all over the world. It's about 15,300 retention curves. We passed them through some quality control. We estimated the parameter robustly. I don't want to spend too much time on this. And then we basically estimated using, we call it geotransfer functions, where we add local clay, local climate, local vegetation, and so on, to map out these parameters globally. So there is a paper somewhere here, scientific data, if you are interested in that. But of course, we're not the first. Others have done it maybe less rigorously, maybe less data sets, less global coverage. So there is a US data set from ANSODA database from the Salinity Lab, or the Soil Survey database, which is actually getting better nowadays, but it's still just the US. So if you're doing stuff in Europe, in Siberia, you probably need something else. Okay. So I wanted to talk about adsorption and capillarity in soils. So I'll just mention very briefly the concept, again with Marcus, of calculating what is the average thickness of film on flat surfaces as a function of water potential. It turns out that the relationship are relatively simple, algebraic almost, using just van der Waals forces. There are other forces that can contribute, but this is the dominant one. So if you know something called the Hamaker constant, which is roughly, for many soils, 10 to the minus 20 joules, you basically know how to calculate the film thickness as a function of water potential. And you can decompose a water retention curve to the adsorption component and the capillary component. So that's kind of one of the aspects. But then a few years later we said, oh, wait a minute. If I can do that, why can't I invert the dry end of the characteristic curve and estimate the surface area of soils, which is really unknown for many soils. And just to show that this is actually working, we can take data from completely different soils with different surface area. Once we scale them by the surface area, we get one curve for the film thickness of the water potential, which means from adsorption point of view, these soils are very, very similar. And so you can take it a step further, measure the metric potential at and water content at for different soils at the dry end, and calculate based on this equation what the surface area should be. And you can see that for a simple measurement like done with this WP4, just taking a sample and sticking it in and get a measurement, the estimates are not too bad. So I think I'll stop here. Yeah, I just wanted to give you a bit of flavor of capillarity. I missed a little bit talking a bit about microbial life, but I'll leave the lecture available, so for those who want to scroll down can look at it. And also a bit about the mechanics. If you really want to see paint dry, you can look at those interfaces kind of drying between two grains. It's really fascinating. Okay, thank you. Yeah.
A question. Thank you for the nice presentation. I was wondering, so you were speaking about contact angle in the beginning. So we usually measure it on a free surface. How does it relate to contact angle measured inside of the confined spaces like capillaries and so on?
That's a very good point. We tend to think that it doesn't matter, but I think it does, because even if you tilt, if you do a sessile drop and you tilt the surface, you get differences in contact angle. So contact angle is a useful concept, but it may it's not as simple as it sounds. So, but conceptually, the fact that you can even measure a quantity that has origins in the molecular scale is already quite remarkable, I would say. Yeah.
Just to follow up, can you say something about dynamic contact angle?
Ooh, yeah. So what Ron is alluding to is that depending on the capillary number, I'll get different types of contact angle, or if you can imagine a drop sliding on an inclined surface, it will have different contact angles, say in the front versus the back. And so there is some dynamic aspects to the contact angle which are important for displacement of blobs and other objects that are forming in porous media for oil recovery and so on. So I didn't talk about it. There is a whole bunch of literature how this not only exists but also how does it play out in terms of retention of water. We even measured what are the acoustic emission of this contact line as they rush down rough surfaces and so on. So it's a very rich field, but I think if you guys got the concept of contact angle, I'm super happy. Sorry, yeah?
We've got one really cool graphic, which almost looks like a water table with soil above it, and you see the jumps of water, and they form in like little patches randomly distributed. I didn't see any of them go back down. Do they stay indefinitely? Is that a fact? Like,
that was a conversation I had with Kevin earlier this week. If I increase the rate of drainage and I trap more, and we are guaranteed to do that, so it doesn't mean that these pockets of liquid that are left behind are in equilibrium. They're not. And so what you'll see is that later on, either there'll be film flow that will balance the potentials within the domain, or vapor flow. One would happen at shorter time scales, the other will take a bit longer time scale. So you may have not seen it because I have not presented it long enough, but we did acoustic emissions, and when you do the drainage, you get certain amount of emissions during the drainage. It was the little part. The long part, all the popping happened hours and hours after. So it's a very good point. The relationship between the phase entrapment and the state of equilibrium is a very interesting one and a complicated one. But intuitively, we understand that when we pull water fast enough, we rip all these interfaces that are not in equilibrium, and then they'll reach equilibrium if we give them long enough time. Otherwise, you know, it will reach equilibrium. There's no otherwise. It's just going to take some time.
Just to comment to that, there is like one paper, I think, that they measured it months later, I think by mistake, and they actually saw that there is some kind of a thermal instability that continues. It's a different region, it's not a washable.
Yeah, and it just reflects on the fact that when we have drainage and ripping of these interfaces by this relatively violent motion of displacement fronts, we are far from equilibrium. So all this creep flow that we assume in the equilibrium zone is not, it's not the case. And so that's, I think, is something that's a take-home message from this type of experiment. All right, Kino, are you ready?
I mean, I don't know, after you, that would be...
Oh, yeah.
I would just like to give a special thank to Dani because he's, well, not only a lecturer to this summer school, I mean, he's been really dedicated also in the organization with funding and also with the scientific program, together with John Selker, who will arrive later. So, Dani, thank you very much for the
Thank you.
dedication to this summer school.
Thank you.